Alright, so let's start working through some of the word problems around that worksheet. There's a nice mix of problems on there, and some of them might look familiar to you based on ones we did in class. Some of them might look unfamiliar completely. So just to be safe, we'll go through all of them. And again, hopefully you've tried them all first before you come here looking for the solution. But if you get stuck, that's what we're going to go through. We're going to go through all of them. So for the first one here, a community recreation center, they want to enclose a rectangular swimming area to public beach. They have 300 meters of rope and buoys to mark off the area. And it says, what is a maximum swimming area that can be enclosed along the beach of 300 meters of rope? So what are the dimensions of the swimming area? So the big thing is here, we want to enclose a rectangular swimming area along the beach. So picture what we have going on here. We have some sort of beach that we're going to put in yellow over here. And there's going to be a rope going off into the water. So it's going to be rectangular in here. So we're going to have rope going along like this, so the rope is only going to cover 3 of the 4 sides. So this is what we're trying to rope off. We have 300 meters of rope to do so, and we don't know the dimensions. So let's just label the dimensions something. So it would make sense if we labeled the length L and the width W. Okay, so keep in mind you should always have let statements on there, so let's put some in. Okay, so there you have them. So let L represent the length of the swimming area in meters, and let W represent the width of the swimming area in meters. Okay, so there's a lot we don't know here. So for me, a starting point is it says we're looking to maximize the swimming area. So how do you maximize the area? Well, first of all, the area, as you know, of a rectangle is going to be equal to length times width. Okay, and that's the equation I want to work with to try and maximize, but again, the problem here is we have too many variables here, so we can't do a lot of work with this aside from trial and error. So we need to only have one independent variable. We have a dependent variable of area, but 2 independent variables, length and width. So we need to try and eliminate one of those variables. So the only information we haven't used yet in the problem is that we have 300 meters of rope. So we have 300 meters of rope to enclose this entire area in here. So the 300 meters is going to make up the length and both the width. So L plus 2W is equal to 300. And with this information, we can actually isolate one of the variables. And it doesn't actually matter which one, but usually you want to isolate whatever one's easier. So I'm going to isolate L here, and to do that I'm going to subtract 2W from both sides of the equation. And what I wind up with is the fact that L is going to be equal to 300 minus 2W. And again, the whole purpose of doing this was so I can now replace the L in my area equation and hopefully eliminate that variable. So what this is going to wind up being now is I'm going to have my area, and it's going to be equal to, instead of L, 300 minus 2W times W. Okay, and once you're down to only having one variable here, hopefully this looks a little bit like factored form. Because from factored form, what can we get? Well, we can get the zeros, and from the zeros we can get the axis symmetry. From the axis symmetry we can get the maximum. And since it's asking for us to maximize the swimming area, the moment you hear that word maximum, you know it's something to do with the vertex. So it asks for the maximum swimming area, which is the optimal value, and it asks for the dimensions of the swimming area, which means we're going to need the axis symmetry. So we're going to need everything to do with the vertex on here, so we're going to have to find the zeros. So to find our zeros, again, look at each factor here, set equal to 0 and solve. So we have 300 minus 2W equal to 0. And this one's a little bit easier. It's just simply W equals 0. So that one's already done, thankfully. Here we have to do a little bit of work, so we get 300 is equal to 2W. So W is going to be equal to 150. Okay, so once you've got those 2 zeros, you're off to the races. So, again, just to give yourself a picture of what's going on here, we have zeros at 0 and 150. Okay, we're looking for a maximum, so we know it opens down. So our maximum area is going to be somewhere here, and we know it's going to happen at the axis symmetry. So we can find our axis symmetry here. It's going to be halfway in between our zeros. So W equals 0 plus 150, all divided by 2, which as we know is equal to 75. So what that tells me is that a width of 75 will give me a maximum area. Okay, and so once I know that width, I can find the length as well. So easiest way to do so is probably just go back and use this original equation I used over here. So 300 minus 2 times 75 will be equal to my length. So that is 300 times 150, so that means my length will be 150. So the length is 150 and the width is 75. We're going to have our maximum area. What's that maximum area going to be? Well, we know that area is going to be equal to length times width. So length is 150, width is 75. Multiply those together and you get your maximum area. So it's 11,250. And of course our units will be meters squared. Okay, so does that match the answer that we were given on the worksheet? Yes, it does. So again, the big thing here is you set up an equation, there's two variables, you need to try and eliminate one of those independent variables by using more information, creating a second equation. And you're looking for something to do with a maximum, so you find the axis symmetry, you find the vertex, and then gives you everything you need to know there. Okay, so that's one down. Let's try another one. So in number 2, we have a glassworks that makes lead crystal bowls and has a daily production cost in dollars given by that equation. And so the cost C depends on the number of bowls made, which is B. So it's already defining your variables for us there. How many bowls should be made to minimize the production cost, and what is the cost of this many bowls are made? So again, our variables are already defined for us, but it says how many bowls should be made to minimize the production cost. See that word minimize there, you know it's something to do with the vertex. Okay, does it make sense to be a minimum? Yes, because we have a parabola that's opening up. So how do we find, so it's asking us how many bowls we made to minimize, so it's asking us for the B value, okay, and it's also asking us for the cost, so it's asking us for the C, so we need both the independent and dependent parts, dependent variables that give us the minimum, which means we're dealing with the vertex. So what's the easiest way to find the vertex here? So you have C equals 0.2b squared minus 10b plus 650. So to find the vertex, you have a couple different options. One option is you can try and factor it to find the zeros. So you can use the zeros to find the axis symmetry, and from there you could find the vertex, or the optimal value. Okay, the problem you're going to find here is if you take a look at the discriminant here. So discriminant, if you do b squared minus 4ac, again, don't get confused with the b here being the independent variable and the b is in the coefficient of the b term from standard form. But this is going to be negative 10 squared minus 4 times 0.2 times 650, which if we do a quick calculation on, will tell you that's going to be negative 420. And the fact that the discriminant's negative should remind you that there's actually going to be no zeros. So that method that I mentioned, to use the zeros to find the axis symmetry, is not going to work. It's because you won't be able to factor it, and even if you want to use quadratic formula, you're not going to get a solution out of it. So the whole idea of using the zeros to find the axis symmetry will be completely useless to us. So much for that idea, which means that we need to either we put this directly into vertex form by either completing the square or using partial factoring. So those are both methods as well. Okay, so if you like either of those, you can put it into vertex form and get your solution from there. Clean the square or use partial factoring. Okay, but the easiest way to get the vertex from standard form, in my opinion, would be that method that I showed you guys in class that reminds you that from standard form, the axis symmetry is just going to be x equals negative b over 2a. Okay, we derived that when we were talking about partial factoring and completing the square from a general equation in standard form. So you can use this to get the axis symmetry. Now, you got to be a little bit careful with our variables here. Our independent variable is an x, is actually b. So in our situation here, our axis symmetry, it's going to be negative 10, to of course simplify to plus 10, over 2 times 0.2. Okay, so run that through your calculator, and it's going to be 10 divided by 0.4, which is 25. So that's our axis symmetry. So that's telling us that when 25 bowls are made, you're going to get our minimum production cost. So which is great, which gives us part of our answer, but then it asks what is the cost when this many bowls are made. So how do we, so that's asking for the optimal value. So when b is equal to 25, what's the cost? So we can just run that, sub that into the equation and solve for c. So we get 0.2 times 25 squared minus 10 times 25, all plus 650. So let's see what that gives us. So I get $525. And matches what we got there. Okay, so again, this one was just asking us for the vertex, and again, it just depends. You're not being asked for anything new here, right? We spent a lot of time finding the axis symmetry and vertex from standard form, just being asked to do it in a word problem context. So you can't rely on always being able to use quadratic formula or factoring to get your zeros to find the axis symmetry, because sometimes that doesn't work, and this is one of those situations. You need to be able to have ways of getting the vertex directly from standard form. So completing the square is an option, partial factoring is an option, or using x equals negative b over 2a to get the axis symmetry and find the optimal value from there is an option. So you need to have those tools in your toolkit, so to speak. Okay, so that's a good place to stop for now. So I'll continue working through this worksheet in the future videos. So if you need help with anything else, we'll see you over there.